Okay, welcome everybody. It's our pleasure to have Zach Furman to tell us about circuits from the top down.
Hey everyone, so as Ben said, it's a good from the top down. So this is going to be not mainly not original work, but more of a synthesis of some existing work that's on this topic. So going over some stuff from some existing deep learning work, some existing work in Boolean circuits and circuit complexity literature, the other thing before I start is that when I say circuit, a lot of people in mechanistic interpretability might assume that immediately what I'm talking about is something about neurons or things like that, or directions and activation space and things. And this is I'm not necessarily assuming that, though there is a connection to that thing, but just a preface. Okay, so we'll start kind of with the big question of why deep learning even works in the first place, and specifically, you might want to ask, why can it even fit the function I'm asking it to fit in the first place? Not even why it generalizes, but why can it fit the function I asked it to fit? And the traditional answer is universal approximation. And here's the, I don't expect you to read this, but you've probably seen this before, but this is the actual statement of the theorem for the arbitrary width and bounded depth case. But there's a little bit of a problem with this, in that, well, it's not a very specific property. So like lots of other things are universal approximators, and they don't fit, a lot of this data very well. Fourier series is a universal approximator. A wavelet series, polynomial approximation, all of these are universal approximators. So
when you say don't fit, you mean it's hard to learn, I think.
Yes, theoretically, with enough Fourier terms, you will approximate every function to arbitrary, every like Lipschitz.
My billion-degree polynomial will do just as well as GPT-4.
Exactly. Yeah. So something else must be going on here in order for them to be able to represent so much efficiently. And actually, if you look at the theorem right here, so this is like incredibly important, is number of neurons k large enough. And this is very load bearing. So most obviously, if you just give me as much space as I want, I can just use a big lookup table. It takes exponential space, n to the k, where k is the resolution I choose to discretize at. But every single input dimension, this will be exponential in space. And actually, this is in fact true of universal approximation. So for generic Lipschitz functions, the number of neurons required for universal approximation is exponential in the input dimension. When you go through the proof, it does this by constructing and summing basis functions and basically creating an interpolated lookup table. So this is like a very direct connection. And so that means that there has to be something special about the functions that we care about in order for them to be represented efficiently without taking more atoms than in the universe or whatever to approximate. So I'm going to talk about some hints about what kind of properties they might have from first just going through some deep learning evidence. So one is sort of most obviously related to the title they talk, a lot of the stuff from mechanistic interpretability. So the original name for circuits in this context comes from work by Chris Olah in looking at image models, and you can see this kind of like hierarchical thing where like wheels and car body and windows and stuff are used to construct a car detector hierarchically. This is something more specific than what I mean. There's something more general that I'm kind of trying to gesture at, but this is an example of the kind of thing you see. Another example, so this is more on the theoretical side, is these theorems called depth separations. So there's a ton of these. I just picked Rolnick. This is showing that there are some classes of polynomials, and this particular one is monomials. Monomials take exponentially more neurons to approximate with a shallow network compared to a deep network. And right here, this this term right here is the single layer case. This one here is the deep case, and right here you can see it's a product of those powers in the monomial. This one is a sum of logs. So this is just a log, roughly up to some factors. This is basically the log of that. So there's an exponential gap between the two. And when you go through the proof, you find that the central property being exploited here is the hierarchical structure of the polynomials being approximated, is being exploited in order to give you these like non-generic bounds that specialize in the form of deep networks. So again, we see this hierarchical structure of the problem is highly important in terms of your ability to represent it efficiently.
So what was the M uniform?
The M1 uniform, or the first line or the second? The second one is the deep. Second one is deep. The amount of neurons for a deep neural network to approximate this.
Is it on weight so much?
This is. I think this is. I'd have to check on that, but I think it's one of the two. I think it's the amount of neurons, but I'd have to check. Yeah.
So what is that amount of neurons?
This one is the product. So there are the powers of the monomial there, R1 through N. So this is the product of them, whereas this is the sum of the log, the sum of times some factor and added by a factor. But it's basic. This is a product of those. This is a sum of logs, and so this is the log of a product is a sum of logs. So there's a logarithmic in the other direction exponential gap between the two of them.
Between what and what?
The number of neurons, right? This is
In the deep case, in the shallow.
in the deep, sorry, yes, deep versus shallow case. Yeah, this is deep. The number of neurons for a deep neural network. This is the number of neurons for a shallow.
I see. Okay.
Yeah. So another thing that Yor spoke about the other day was about simplicity bias. So this is from this paper actually. And right here you can see LZ complexity is a measure of the you can think about it as a complexity measure of how efficiently it's related to how efficiently you can compress something. And you can see that the probability, the log probability is directly related to the LZ complexity. So empirically, this is something we observe at least for small models. A feature of a function being expressed, I believe. Yeah. And I don't remember exactly how to measure that in terms of what constitutes a function.
Sorry, this is the LZ complexity of what?
Of the function that is being expressed by them.
Okay.
Yeah.
In the first graph, what is the rank of one?
Yeah, I should have cut off this. I just lifted it from the paper, but I should have cut that off because the point was the one in the middle. And then SLT itself seems to point to this, something in this direction as well. So Watanabe mentions in the gray book, he mentioned this multiple times throughout the gray book and the green book, about how singular models often have hierarchical structures, that when you have hierarchical structures, you tend to get singular models. And this is not necessarily like an equivalence, like there are singular models which are not hierarchical, but these two things often come together. And another piece of evidence from the SLT side is studying degeneracies in single layer ReLU and single layer 10H networks. So I have something from Matt's thesis here, which is showing how degeneracies in one layer 10H networks correspond to places where you can continuously, these symmetries where you can change the parameters of the function of the network without changing the function it implements, all the way up until you get a dead neuron. And so every one of these degeneracies in the one layer neural networks where we have these full classifications, we know corresponds to essentially effectively smaller networks. They could be expressed, the function could be expressed with fewer neurons. So we see this connection between, SLT is showing us a connection between structure, the sort of structure of the kind of structure of the function that neural networks implement is very central. Now I've talked about some empirical and things specific to deep learning, and now I'm going to step back a little bit and just speak talk on an abstract level, right? About how is it that we even manage to do better than a lookup table, right? We clearly manage to compute things all the time, both humans, us as humans, and computers. How do we even manage to compute things tractably? So you can think about adding some numbers. So if I have if I'm adding, 3 numbers together or 5 numbers together, I could have a big lookup table with 5 different sides, 5 different dimensions, and each one corresponds to the exact addition, and this will be really expensive to store. It'll be exponential to store. Or I can have a lookup table for only each addition that I do, each adding 2 numbers, and then I can do this hierarchically to compute adding of any arbitrary list of numbers without needing to memorize the whole thing. So we break problems down step by step and piece by piece. And the way you can formalize this is with Boolean circuits. Here's an example of a Boolean circuit. A Boolean circuit is basically, for those of you who don't already know, it's just a function that basically it takes in ones and zeros. It's this kind of graph structure, and each time you hit one of these gates here, it does a little mini lookup table, which is just a little they're only a little mini lookup table, and it will just spit out a number here, so it'll be like an AND gate or an OR gate or things like that. And this is a non-uniform model of computation, so it has a fixed number of inputs. But what we actually say is that this is equivalent families of Boolean circuits, and you have to talk about families because they have a fixed number of inputs. But families where they have different number of inputs are equivalent. Poly-size families of Boolean circuits are equivalent to problems in P. So any problem we can solve tractably in polynomial time, it can be solved with a P uniform, which is just this condition that you actually can generate this with a polynomial time Turing machine, which just prevents pathological examples. But P uniform family of Boolean circuits, which have size and polynomial in their number of inputs. And here what you see is the hierarchical structure of a problem gets reflected in that Boolean circuit family. When you look at the XOR gate, you did addition mod 2, and that's a bunch of XOR gates. It's a tree of XOR gates, and you see the exact way in which you break the problem down gets reflected in the actual structure of the Boolean circuit family. And this is sort of intrinsic to the problem itself, that it has this decomposition. Not all problems do. So there's maybe one kind of abstract lesson that you might take away from this about that learning in a tractable way, in a space-efficient way, requires figuring out how to decompose a problem down into problems small enough to be memorized. If you want to be space efficient, this is sort of the informal statement of what that Boolean circuit equivalence is basically telling us. Now, this is still just an analogy to neural networks, but we're going to continue it a little bit and see what other things we might see. This is the difference between NC. So we're going to look at NC0 and NC1. NC0 are the problems that a basically constant depth Boolean circuit can solve in polynomial time, whereas NC1 is logarithmic depth, and we have that NC0 is not equal to NC1. It's a strict subset. This is via AC0 and NC1, which is the more well-known result, but is less obvious exactly what this is showing, because what you can see here is this parallels some of the, similar to the depth separation results we saw earlier. There are very similar results here, because this is actually an exponential gap it's showing us, because you have to basically relax the polytime condition in order for these to be expressed as much as these. They can express as much of these just with exponentially more size.
Sorry, Zach, maybe I'm misreading this, but uniform Boolean circuits in fully time, we saw already, that was equivalent to P. right? Or not, I mean,
No, it's constant depth, so they're limited in depth.
oh, so it's below P, much below.
Yeah, this is pretty limited.
I see, isn't it over?
No, this is equivalent to AC0 and NC1. P and NC is an open problem, if that's what you're thinking of, or the NC hierarchy is also an open problem. So NC1 equals NC2 is unknown, but NC0 does not equal NC1.
What does logarithmic depth mean in this context?
Yeah, that's good. So it's O of log n of where n is the number of the input size. Yeah. An example of this would be like parity. Parity function on Boolean input scores logarithmically with the depth of the circuit to compute it with XORs. And that can't be computed by something in NC0 in polynomial
Is the
size.
depth of the circuit the maximum like number of sequential Boolean operations?
The depth of the circuit, yeah, it's the essentially it's the number of the maximum number of sequential operations in the tree, basically. Yeah. So, and this is quite similar to what we see in neural networks. It's kind of suggestive that we see something quite similar. And in fact, the people who proved the original depth separation results were inspired by some of the results in Boolean circuits. Another thing we see in circuits, in Boolean circuits, this one has a little bit more of a speculative connection to neural networks, but it's an interesting one. So the time-bounded homographic complexity, KT complexity, of a function's truth table is bounded both above and below by its minimum Boolean circuit size. So this is from Allender in 2005, and you get this expression involving the circuit size and the length of the string of a truth table of a Boolean function, and you get an upper and a lower bound. So the upper bound is not very surprising, but a lower bound is that nothing, and basically that knowing the minimum circuit size can actually tell you that something can't be done faster, substantially faster than some lower bound.
Briefly what time bounded come over.
Yes, yeah. So this is the program size times its execution time. It's not time bounded, but people call it time bound. It's like time penalized.
Okay.
More like.
And there's a variant that takes log of time.
Yeah, there's a variant. So K little t complexity, which is the program size times log of time, and it's like equivalent to like KT complexity if you have like an exponential like oracle or whatever, basically. Or it is not. It's equivalent with the exponential.
What's an exponential oracle?
You can basically solve you should solve problems in exponential time. Specifically, it's like you have to say like 2 to the n time or whatever, an oracle that can solve all problems in 2 to the n time. I mean, it's just the fact that you can get rid of the logarithmic difference by giving it an exponential speed boost, basically. But that's the relationship. I don't know more than that. I think there might be more connection. But what's interesting is for Boolean circuits, selecting small circuits is the same as selecting simple functions. So the speculation is, so we saw that, yes.
Sorry, just that last line, that's your interpretation of this result.
Yes, and it's a little bit,
You're using KT as like the measure of simple functions.
yes,
And
yes.
You're saying small circuits, simple functions line up because of this result.
Yes, yeah, and technically, like you could pick, you could pick a small circuit that happens to have like an even smaller circuit. So like, but for the most part, like this, you can think of that like as a decent takeaway from that result. But the speculation is, and we observe some simplicity bias in neural networks, that if there is some mechanism which causes some kind of modular hierarchical structure that's similar to Boolean circuits, that given the kind of the connections we already see between Boolean circuits and neural networks, that it's plausible that this connection could carry over. Speculation.
So which way is this connection going?
Which connection?
The connection between neural networks being the simpleness Boolean circuit thing you're showing here.
So this is just an analogy. So there's no, like, it's just, we see Boolean circuits have similar kind of like properties to some of these things I sketched out. And like, we see some parallels, but there is no like proof of this.
Okay, I'm sorry, I'm stupid. Can you tell me what like exactly the analogy is and how this is relevant to neural network?
Yeah, so that's my next slide.
Okay.
But
sorry.
yeah, it's
Just quickly, you're saying speculatively, concretely, you're speculatively conjecturing that a function that can be well approximated as a small deep neural network, that would give you a lower bound on the KT complexity of that function.
I think that's like the rough intuitive thing that I would expect, but I think there's technicalities there about exactly how to express that. Yeah.
Can I clarify when you say KT complexity of a function? Is that function sort of completely implemented by the algorithm, or is that function a mathematical function?
So sorry, KT complexity is of the truth table. Like the
I said KT complexity of a function. Sorry.
Yeah. Sorry. It's you have to. It has to be of the truth table. Yeah. So, what does this say anything about neural networks? So there is a trivial way in which it applies, in that neural networks are implemented in a computer which functions with Boolean circuits, but this isn't very helpful for us. So is there a non-trivial way?
Is that not helpful? Sorry.
Well, I mean, it tells us that like neural networks, don't run in exponential time, basically, but we kind of know that.
Does it just give you not a useful bound?
Yeah, I mean, it's just like the Boolean circuit structure of the neural network kind of boils down almost to like the structure of the neural network itself. Like,
Yes.
so it doesn't. Plus some stuff you have to do to like discretize it and all that.
What if you deeper neural network, the cost of learning the Boolean function?
Yeah, so there's some people have done this. You can also like binarize a neural network where you like quantize it down. I don't know if I can say if I remember exactly what this found, but I know people have done this.
I still don't really fully understand what all this Boolean circuit property is for. Is it really something like we observe that neural networks implement simple functions, and we know that simple functions correspond to simple Boolean circuits. So if we find circuits in neural networks, they will probably be simple.
This is no. So I'm not. I think that's so. I think this is more the Boolean circuit stuff is I think more of a illustrative kind of parallel. So I think this is an area where we have like well-developed kind of theory, and like these things parallel some results we see in neural networks, but there is no rigorous connection at the moment. And to the extent that I expect there will be, I don't expect it will be just transferring Boolean circuits to neural networks. I think Boolean circuits are probably not the right formalism for reasoning about neural networks. I think you want to use things that are a little more like probabilistic and stuff like that.
So the parallel was simple circuits implement simple functions. So simple neural networks implement simple functions. Is that the parallel?
It just suggests like
just the case you want to say the inductive bias of neural networks is that it learns simple functions. That's an intuition, and you want to back it up with
Yeah, we know, we sort of experimentally observe this simplicity bias, and you want to be able to explain this in some way. And in the Boolean circuit case, there would be a rigorous explanation for this. In the neural network case, we don't have that, but
So if you could connect the two
Yes,
worlds, you'd
exactly.
be able to explain the observed
yes,
inductive bias.
exactly, yeah.
Is there also a story like, you see the neural network implementing a simple function, and like the general neural network could be represented by like in general a very large Boolean circuit, but because the function is simple, we expect there's like some smaller Boolean circuit that corresponds to what the neural network is doing, and in other words, like there's some like more simple circuitry inside the overall neural network, and the overall neural network is like much more general than the thing that we could have had. Sorry, than the actual thing. It could, in theory, be much more general than it is in practice.
Yeah. I mean, so I think there's something there that I would agree with. I think it wouldn't be a statement about Boolean circuits, because I don't think they're necessarily the right formalism for talking about neural networks. But I think there is potentially this possibility that I think this is essentially the right. This is the speculative kind of picture I have, is that neural networks have this ability to represent more complex functions, and that there is essentially like almost like sub circuits that basically like are simpler, but this is like very hand wavy in like yes, but I think this is like roughly the right picture, just like Boolean circuits aren't exactly what I would expect. Yeah. Okay. Oh,
Completely trivial. If I give you like a ridiculously large Boolean circuit to then
Yeah.
reduce it to the minimal Boolean circuit that implements the same function.
I don't think, I'm trying to remember. I mean, the minimum circuit size problem is like very hard. I mean, though I think like that's asking an easier problem, like just to make it smaller, which
Well, if you could always do that. Division.
sorry.
The circuit is only n size.
Yeah, but if there's some like for instance, there are ways you can do this where like if there's just like kind of trivial redundancies, like you can eliminate those, but then you get to a point where you have none, and yeah, exactly, yeah.
Optimizing Boolean circuit, not that easy.
What?
That's right.
I think we should.
Yes,
I bet
yeah.
it's easy to find the loop in.
But yeah, I think this is mainly like a suggestive kind of analogy, because we have good theoretical models here. So the idea is like, oh,
Sorry. If you have like a random very big Boolean lookup table,
a Boolean,
like sorry, a very like a Boolean function that's like a random Boolean function at the input.
Yeah.
Is it in like with probability near one not compressible at all?
yes. Yeah, this was, I think Shannon proved that. Yeah, that's one of the few results we have in circuit complexity where we know that something can be compressed. Random Boolean functions can't be compressed with almost certainty. Yeah, there's this open question of whether we can make a rigorous kind of bridge here, and I think it doesn't look like you just take Boolean circuits and apply them to neural networks, because I think neural networks are fundamentally kind of continuous. We see it in singular learning theory. It makes a lot of sense to treat them as probabilistic models. So there's some other formalisms that I think work better, which I don't think I don't quite have time to cover here, but yes.
Are there any similar simplicity bounds on probabilistic circuits? Does it make sense to ask?
Probabilistic circuits. Yeah, I have a conjecture about this, but this is like very
I'll say
not at the moment, but I suspect that there might be. Yeah. This is a suspicion. Yeah, and in particular, the probabilistic circuit in that case would be Bayes nets. So I don't have time to justify exactly why you might use like some of the different formalisms you do. So I'll just mention two possible. Wait, actually, it's the slide up there. But I'll mention just two possible formalisms you might use. that aren't Boolean circuits. One is, if the neural network implements some function, I might want to reason about having a function decomposition of that neural network. Another way you might do this is looking at a Bayes-net decomposition, which seems like unnecessarily complicated, but it has some nice properties, including like it turns it into a linear algebra problem. But I won't go into, I'll go into detail after the talk if you want, but I only had time to cover this. So yeah, so I'll just kind of end with a couple things, the high level kind of path that this might suggest. So the circuits agenda, the traditional circuits agenda that's been pursued in mechanistic interpretability, makes some really good promises about how we might be able to really completely reverse engineer neural networks and understand them to a large degree, especially in terms of the kind of safety properties that we can specify. But historically, this has been very much like a bottom-up approach. Empirically, we conjecture maybe that circuits might be neurons, or they might be made out of features, or maybe they're made of directions in activation space, and you risk this kind of street light effect where you're only able to find circuits that exist in the way you define them or with the tools that you currently have. There are some roadblocks that people are currently working on kind of solving that people may eventually solve, but it's certainly there's certainly challenges with this approach, like superposition, and this approach may completely succeed, but I think a parallel approach that I think has been kind of neglected is that I think there may be a path forward from the top down in a non-constructive definition of circuits in terms of these kind of theoretically expected properties that we would expect them to have with similar kind of reasoning that I talked about in the talk, and the implementation is derived from the theoretical properties rather than postulated in the first place. And this is my kind of current research direction. So I'm just going to end with some couple open problems. This is a very incomplete list. There's not enough detail, but so
Very incomplete list.
very incomplete list. I don't know if I said very complete list.
list.
Yeah, that would
It's
be-
like, that's pretty rare, yeah.
Yeah, that would be pretty crazy. Yeah. No. Yeah. So there's a few. So I mentioned finding the right formalization of circuits. I have some ideas. I mentioned a couple, and this is something currently working out, and don't have exactly the time to cover that, but there's a few other questions that, okay, first, can we actually connect this stuff with deep learning? How does the implementation work? Can we connect this with training dynamics? One thing that's interesting is, I mentioned that degeneracy, the connection with degeneracies and circuit structure. Can we actually investigate that? And how much of this Boolean circuit analogy carries through? Does this simplicity bias stuff, does this kind of thing actually make sense on a rigorous level? So that's it. Yeah.
What sort of level of description and what sort of like implementational constraint would this top-down description of what a circuit should look like?
Yeah, so I mentioned a couple. So the simplest thing you might expect would be, for instance, you could basically say, okay, what we want to be able to do is use circuits to break down kind of how neural networks reason, and sort of ultimately what we care about is that the function a neural network implements decomposes. There's some function decomposition. Now there's a trivial function decomposition, which is the neural network itself, but you're supposing that there is a non-trivial function decomposition. And then from there you start to reason about, okay, what kind of structures in a neural network would be capable of implementing this. I think phase nets might actually be a better formalism than this, but it's kind of still a little bit open.
Okay, so like would the outcome of this reasoning process be some sort of inductive bias for a circuit search algorithm? Would it be like a RASP style? I know exactly how this should be implemented. I can like compile it into a transformer tracer. Yeah. Well,
Yeah,
the RASP is the language and tracer is the compiler. The whole thing was something.
it's meant to sort of guide the search. The one thing like you might want to reason about is like, okay, can this get spread across multiple layers? Like this, what does that mean for like, you know, is it possible, like how possible is it for things to kind of smear class layers? What are the limitations? Like, you know, you have this, for instance, like you might expect there are constraints in terms of order of execution, and like this can constrain and the topology of the network and stuff like this can constrain exactly. Like you can start to put constraints on this, and hopefully one thing you could expect to do is this guides some sort of search that narrows down the search space is one particular way this can go.
Okay, I'll harass you more later.
Not sure if this is probably isn't a question, just like an idea that was inspired by the talk or something. It's like one thing I know you're interested in is like nonlinear circuits and like trying to escape this catch-22 of saying circuits are linear, and also our only techniques for finding circuits are linear. Hey, look, the circuit we found was linear. And I don't know, like it would be cool to be able to do something like in a toy model, use something like one of these definitions to reason about the existence of some circuits, and then like search for everything linearly and not find anything, and then be like, could you imagine something like that working, some variant of that? Like, because like we want to be able to prove the existence of the, like demonstrate the existence of the nonlinear circuit in that way or something.
I think ultimately, like in order to do that, you're going to want to actually show where the computation is happening. My current work right now is in kind of trying to provide a counter example to this like linear features hypothesis. Not exactly in that way, but yeah, I think this is a very hard thing to do. Let me not undersell that, but I think it's possible. Yeah.
Why is it so hard?
It's very okay. So right now there is no rigorous definition of what a feature is. Unless you're going to postulate that these are kind of things that you find linearly. It's just I know it when I see it kind of thing. And our only tools that are good at this right now are linear. Now there's things like nonlinear probing and stuff, but these have problems that make them break, so you won't actually expect them to find nonlinear structures robustly if they're there. So it's one of these things where like, okay, I say that I have a problem that should have linear circuits. This ground truth, the ground truth seems like it should have linear features or whatever. But then, someone can come along and say, well, even though you think you know what the ground truth for this problem is, actually the model could be implementing in this totally different way, and you're just not searching right. So you kind of can end up in this like circular thing. So I think there's a way around it where you actually like, this is going to get into a longer answer, but yeah, that's the difference.
So question.
Yeah.
If you're confident that if you're confident that neural networks should be storing some things non-linearly, then shouldn't you be able to like just manually construct a neural network that does store something non-linearly?
You can, yeah. When people talk about like features or linear hypothesis, it's usually not that it's like impossible to do this.
Sure. But if you can do that, then what's kind of the way that you do that, and do you have a way to search for things that are similar to the constructed thing?
I mean, that sounds a lot like, one of these things is, you can do things where you like construct these kind of like ground truth programs and see like tracer is like that. I don't know if it's really non-linear. But there's a lot of ways that you can make a nonlinear circuit, and so it's. The hard part is that it's like it's very hard to get like an exhaustive list of the ways.
Sure.
Like there's a lot of ways. To do it.
And we should thank Zach again. What's next? Okay. That's it, everybody.
What do you mean by decomposing the network?
Yeah.
That's so cool. Racing, I've never heard of it till just now.
Barely looked at it. It certainly sounds-
Yeah.
Yeah. No,
What was the last take?
I'm glad that the people were actually, at least one person, yeah, more than everyone. Yes, they do.
Colleen.
Sorry. Okay.
I don't know if you can, but can you show me an example of using this from a logical to calculate them?
Think about it like factorization. Okay, an answer is a factorization of probability distribution with like conditional dependencies. No. It's more general. So it's actually they're equivalent to they're factorized factorizations of probability.